Alright, I wanted to make a quick video about how to match slope fields to their differential equations. Now, there are a lot of different ways to do this. One of them is just by picking a bunch of points for differential equations and plugging it in and figuring out what the slope is and then trying to see if you can match that to one of the fields down here. And that does work, but there's a much faster way that's more effective if you'd like to do this for a test, for example, and you want to do it quickly. So when speed is an issue and you already have your slope fields prepared for you, you can completely ignore the differential equations to start. The first things we're going to do are looking just at the slope fields themselves. Sorry, there's my dog. The very first thing that I look for is a slope field with only one variable that affects its differential equation. So I'm going to look just at the first slope field here, slope field A. And what I notice about slope field A, right over here in the top left corner, is that no matter what y value I'm at, all of my slope fields match up and down. So over here at -3, I have the same slope. It's going downhill relatively smoothly. And then as I move towards 0, it's going downhill faster, but as I move up and down, they all match. Nothing's different. Here at 0, they all match. Every x value that I go to, all of the y values match. And what that means is that y values don't matter in this slope field. So no matter what view I take of this on a y value, there is no change to my slope field. That means that in my differential equation, I have no y value for this equation at all because it makes no difference. So I know that the only variable that I have in this particular slope field is x. Because as I go through my x values, things change. I start not so steep, and then I get steeper, negative, and then I'm undefined, and then I get less and less steep in the positive direction. So this is steeper than this one, but they're all uphill, and these are all downhill. So as I move from left to right, there is definitely a change in my slope. But as I move up and down, there's no change. So there's no y value. There's definitely an x value. Let's take a look. What we're going to do is once we know what it looks like to have only one x variable, let's go ahead and find all the ones that only have an x variable. So this one changes up and down, so I don't care. This one changes up and down. We'll skip that one. This one changes up and down. Over here, all the same up and down. For every single x value, it's all the same up and down. That means this one only has an x value. There's no y value that makes any difference to this slope. Over here, it changes. Down here, again, all the same, up and down. So I know that this is an x. Only an x value here. And if we want to continue this pattern, there aren't any more with only x's. These ones change up and down, and these ones change up and down. We can start looking side to side to see if there's anything that's consistent from side to side. So this one we already said differs from side to side. This one looks like it's the same side to side at 0, but if I move up or down, I can see that here it's downhill, here it's undefined, here it's uphill. So that does make a difference. Over here, no difference side to side. No matter where I go, they're all the same. That means that my x values don't mean anything to my slope. It doesn't matter what x value I'm at, my slope is the same. So there's no x value in the differential equation that makes this slope field. So this must only have a y value. If we look for others, this is different side to side. This one we already said only had x. This one, completely the same side to side. We can see that pattern. That must only have a y value. Down here we already said it was x. Here, side to side. They are all the same. No matter my y value, my x's are all the same. I get the same slope along my x values, so this must only have a y. Those are all the ones with all y. As I look at this one, it does change from side to side. So I have my 3 functions with, my 3 slope fields with only x, my 3 slope fields with only y. So these ones left over that change side to side and up and down, these must have an x and a y. So I've drawn a little x and a y. So up here, this one has an x and a y. It changes side to side and it changes up and down. Down here, it changes side to side. At some of the values, it changes up and down for others. It doesn't matter if it doesn't change for one particular value. We're looking at all the values. So in the grand scheme of things, x and y do make a difference for this slope field as well. So once you have that step done, which should go faster for you than it went for me, because you should be able to say up and down, up and down, up and down, perfect, side to side, side to side, side to side, okay, and then this changes. So once you get the hang of that, that'll go a lot faster for you. Once you separate out the types of equations you're looking at, you're going to start by looking at only one variable at a time. So I'm going to start looking at my x variables, my functions that only have an x value in them. And again, I'm not looking at my differential equations yet. All I want to do with these three slope fields is I want to find one coordinate point, one place on my graph, an x value, a y value, x comma y, one coordinate point where all three of these functions have a different slope. So if I pick something over here, for example, in the top corner, this is going uphill, not so fast. This is going uphill very fast, and this is also going uphill very fast. So all of them are uphill. That doesn't give me enough of a difference, and these two are so similar that they could be the same number. I don't know. So those are too similar. What I'm talking about for difference is I want them to be completely opposite. I want to compare uphill, downhill, side to side, and straight up and down. These are the differences I'm looking for. Not different types of uphill, but completely not uphill at all. Or not just, almost straight across, but straight across or with a slope or undefined. So I want to find those differences in these three equations. One of the places that I can do that's easiest for me is actually right here at 0. So right there, that one is straight up and down. That's undefined. This one here, straight across. That's a 0 slope. And this one down here at the origin, that's uphill. So I have three very different slopes at one point. And I've already determined that my y value doesn't matter, and it's true. If I go up here to 3, again, I still have undefined, 0, and uphill. So it doesn't matter which y value I choose, but the x value that I've picked for all three of these is x equals 0. So x equals 0 is going to be the only number I have to plug in for any of these equations. Now, I did say that these three equations only have an x variable in them. So this is when we actually start looking at our differential equations. And we want to look at which variables or which equations up here only have an x variable. So the very first one I see right there, y prime equals x. Y prime is not a variable. That means slope. So my slope equals x. X is the only variable in my slope. So that's one of the ones I'm going to be looking at. The next one down, y prime equals y. That's got a y but no x. This one here also has a y. Here we go, y prime equals x plus 1. So our slope equals x plus 1. That's only got an x. That's another one we're going to consider. And the next one down, this has x times y prime. So I do have to get y prime by itself by dividing both sides by x. And what I end up with is y prime equals 1 over x, which again only has an x value. So this is another one I'm going to consider in this step. So for the three that I've decided to consider, y prime equals x plus 1, and y prime equals 1 over x, all I have to do is plug in the point that I decided was different for all three of them, and they will automatically give me my answer. I will be able to match three of these by plugging in one number each, not a whole slew of numbers and then trying to match it, just one number. So if I plug x equals 0 to my first equation, y prime equals x. So y prime equals 0. So my slope equals 0. Which of these three functions has a 0 slope? That one right there. So this, where the slope was straight across, that's a 0 slope. So that must be this differential equation. So I know that this is equation, slope field E. For the next one that's got only x in it, that's this one right here, y prime equals x plus 1. All I have to do is plug in that same value, 0. If I plug in 0, this tells me the slope of this differential equation is positive 1. So which of these three slopes is uphill, positive? That one right there. Perfect. So that equation must be G. And lastly, I plug 0 into my last equation with only x in it. So y prime equals 1 over x. So y prime equals 1 divided by 0. That's undefined. We draw an undefined slope with a straight up and down line, which is that graph right there. So this one, slope field A, must be equation 5. So let's see if we can do that, excuse me, let's see if we can do that with our xy equations. So I'm going to pick a different color here. Here we go. All right. So on my xy equations, again, start with your equations, not your equations, I'm sorry, start with your graphs, so your slope fields, and see if you can find one point where all three are different. And it's not always going to be here at 0. For example, if I look at these three graphs and try to find somewhere different, if I pick 0, that's a 0 slope or undefined. It's kind of hard to tell in that one. This one doesn't have a line at all, so that could be 0 or undefined, I'm not sure. And then this one down here, again, doesn't have a line, so that could be 0 or undefined. I really don't know for this function at 0, so I'm going to pick a different point. And because I have an x value and a y value in each one of these, I have to pick an x value and a y value. This one I only had an x value, so I only had to pick an x value. For these guys, I have to pick both an x and a y. So I'm going to be looking at places all over the graph to try to find one place where all three of these graphs have a very different slope. So if I go to the origin, it doesn't work. What happens if I go up from the origin? This one's downhill, this one's undefined, and look at that. This one's 0. So let's look at that spot. We didn't have to go very far at all. So that's downhill, that's undefined, and this one over here is 0. So we have one spot. And what's the coordinate from that one spot? We didn't move on the x-axis, so that's 0. And we went up 1 on the y-axis, so that's 1. So we have an x value of 0, and we have a y value of 1 that we need to plug into our differential equation. And if we plug in this one coordinate for each of the three equations, we should get an answer for each one because they're all very different. So let's take a look and see if we can find the differential equations that have an x and a y value. So up here, this one, y prime equals y, that's only got a y value. Down here, y prime equals 2y, still only a y value. These ones only had x's, we already did those. This is 2y prime equals y, that's still only a y value, so it must be my last ones here. There's our x, there's our y, so if we divide both sides by x, we get y prime equals y over x. All right, that's perfect, so we're going to focus on that one. This one here, again, we need to get y prime by itself. We're going to divide both sides by y, so we're going to end up with y prime equals x over y. All right, there's another one to focus on. And last but not least, y prime equals x minus y. So all three of these have an x value and a y value. And I've picked an x value and a y value to plug in. So let's start with the first one here and plug in this one coordinate pair. So 0 for x, 1 for y. X is on bottom, y is on top. So this is going to be 1 over 0. That's undefined. Undefined, again, is that vertical slope. So we just look at these and figure out which one has the vertical slope. It's right there. This one must be B. There we go. For the next one, x divided by y, I've got my x is 0, y is 1. That's 0 divided by 1. Anything divided by 1 is itself, so 0 divided by 1 is 0. Awesome. So that means that this is a 0 slope, which is that straight across slope. So which one of these has straight across? That one right there. I is straight across, so this must be I. Awesome. Last one, y prime equals x minus y. We plug in 0 for x, 1 for y. That's 0 minus 1, that's negative 1. And this one is downhill, negative 1. Perfect, negative 1's going downhill. So this one must be graph D. This will work for all the ones that have different slopes everywhere. Now we have one more case where we don't have different slopes everywhere. There are slight differences, but they're not completely different. So the y variables on here will give us that difference. So let's go ahead and take a look at those. So we have 3 graphs with y in them. They're the only 3 we haven't matched up yet. So what we want to do is, take a look at the ones with our y variable in there and see if we can see the difference in these 3 graphs. Now there won't be any points where our slopes are going in different directions. With these 3 equations, they're actually almost the same. We still have uphill to the left, or uphill on top, downhill on bottom for all of these. And there are no differences between them except how steep they are. So let's take a look at what that means. This graph has steeper slopes everywhere than this graph. This one's going uphill faster. Like if I was a little dude walking along that little dashed line, I would get out of breath a lot faster than this guy would because I have to go uphill much faster down here. Now, if I compare these 2 guys down here at the bottom, if I was a little guy walking on this line up in the top right, I might get out of breath faster than this guy walking on the bottom left on graph H because this one's steeper. So we have less steep, medium steep, most steep. So let's take a look at most steep. Most steep means that whatever my slope is, it's getting bigger, faster. So my slope here is being multiplied by something. It's getting bigger. So let's take a look at our y equations. I've got y prime equals y. Here I have y prime equals 2y. And if we take this guy and solve for y prime, we have to divide both sides by 2. This is y over 2. So this is y by itself, y being multiplied by something, and this is y being divided by something. So this slope makes things bigger. This must be the one that's being multiplied by something. That's a bigger slope. So this must be graph F. And the one that was the least steep, this one here, this slope is smaller. That means this slope is being made smaller through division. So over here, our y is being divided by 2. So we have half the slope here that we've got over here. That means this one must be number 6. That's h. And our last one was right in the middle. This was our baby bear, just right. So that's going to be equation 2. So graph C for equation 2. And that's all you have to do.